Okay, in this video, I'm going to be talking about rectifying AC. You can't tell that's what this word is. This is rectifying. So before continuing on, right, in this video, you need to know about AC. You need about know about diodes, Zener diodes, and capacitors. So if you don't know about those, I actually have videos on all those topics. So you should, if you don't know, you should just don't know them. Just pause the video now and then get on with it. All right. So rectifying AC. What does it mean to rectify AC? So normally AC, as you should know, it goes like this. So this is voltage against time, right? And then this is AC. It periodically goes from positive to negative to positive to negative. For practical uses, this is completely useless. We can't really power anything, any components with this. We can't like power an LED, a buzzer. I mean, we can, but not to the way not in like we can power it, but okay. Just know that AC is not really that useful, other than for transporting the voltage itself. So we can rectify the AC to turn it from AC into DC. So it is actually possible to turn the alternating current back to direct current with just a few components. So without further ado, let's begin. In this video, I'm going to be talking about two ways to rectify AC. The first is with the half wave rectifier, and the next way is by the full bridge rectifier. Yeah, so let's go to half wave first. In the half wave rectifier, oh, and this symbol here, it just means that this is a AC power source. Yes. So, okay, the half wave rectifier is probably one of the simplest rectifiers out there. All it is one diode, and that's it. So, the diode, as we all know, it lets current flow through one way, and it opposes current flowing the other way. In other words, it can also be defined as the diode allows positive voltage to go through, but not negative voltage. Recall that AC is a voltage, right? Or a signal that goes from positive to negative periodically. So basically, in this half wave rectifier, we delete the entire negative portion of the AC wave, AC signal. So we can see it here actually. The the output of the AC power source can be seen here. So you can see it's a sine wave going from positive to negative periodically. And the output of this half wave rectifier, V out, is this yellow graph here. And we can see that only half of the wave has made it through, whilst the rest of the wave, the negative bit of the wave, has disappeared. Hence, it is known as a half wave rectifier. So, I mean, that's pretty much it. There's not much else to explain in this one. One thing to note that is that if let's say this was a 100 volts AC power source, then this would be 100 volts. This would be a negative 100 volts. So that's simple. However, in V out, the output here is not 100 volts. Recall that every diode has actually a forward voltage, a voltage that's necessary to power it into forward bias, allowing the current to flow through. And in most cases, the forward voltage is usually 0.7 volts. So let's say this diode has a forward voltage of 0.7 volts. So in order to allow current to flow through this way, 0.7 volts from this 100 volts is actually required to allow current to flow through. So in this case, the peak voltage here is not 100 volts, but rather it is 99.3 volts. So we just minus the fault voltage away. Another thing to note with this waveform, the output waveform, is that here it starts here, then it goes negative here, and it ends here. So it's all very distinct points. If we follow these green lines up, we notice that the place marked where the wave should end, so it should end like this. It should end like this, should end like this, but it doesn't. There's a little bit of free stuff here. So what's going on? So in this bit here, we can say that that bit here was actually 0.7 volts. So the moment the supply voltage goes lesser than 0.7 volts, then nothing will be powered. And in these blue cases here, that case occurs. And since it is lesser than 0.7 volts, there's no voltage at the output because there's not enough voltage to power the diode. And that's why there's these little bits here. And this is important, yeah, please do not miss this out. So that is the half wave rectifier. The next bit is going to be a lot more complicated than this. And that is with the full bridge rectifier. So let me just get on with it. Alright, this is the full bridge rectifier. As you can see, it's much more complicated with many more components. I guess there's nothing to do but just get started. So we start with the power source. Okay, this is 240 volts AC, and when we measure the voltage across the AC, the AC power source, we can see that it's a sine wave. 240 volts peak voltage, peak to peak is 480 volts. Yep, pretty chill. And then we move on to the first part of rectification. In the half wave rectifier, if we look back, we can see that only half of the wave has went up to the positive side of the voltage. You see the bottom bit is gone. Well, in the full wave, full bridge rectifier, that bottom bit actually goes to the positive voltage. It doesn't get lost. And this happens in this diamond shaped part here. So you could just memorize this and say, okay, yeah, when the exam, when they ask me, oh, how do I draw this bit, I'll just remember. But I think it is more beneficial to understand how this diamond of diodes actually lets all these hills here get transcribed into the positive part. So let's start. So let's say we are in this part here now. So voltage is positive, so let's just say the voltage goes like this, the current goes like this, and then it comes back. Okay, so that will mean that the voltage reaches this node here. So now we need two diodes. For the left one, the current actually can't flow here because it's blocked by this bar. So the current has to flow through this diode. So once we reach this diode, we actually meet another node. And we can go either way, and in this case we go both ways actually. We go here and here, but let's follow the diamond first. Alright, then we reach this node again, and then we have a choice again to move here or here, and in this case we go both ways. We go through here, we reach this node, and then we can go either here or here. So in this case, when we go here, and note these two bits here. This is actually the V out, which we see where we see this. At this node, there's something I haven't addressed, is that it can go back here. And in this case, I suppose it can, but even if it does, like the current here will be pretty small after going through all this crap. And then just know that it pretty much ends its journey here.
A spontaneous right hand said, check the chat, you are wrong.
Oh, Lamau, yeah, there was something weird about this. Okay, so that was obviously a trick question. Yeah, that was obviously a trick question, because if you were listening, you would realize that this is completely wrong. So if you realize that, then congratulations, because you passed the test. Good job to you. Passed the test. Everyone loves you. And you're a very smart person and everyone gives a shit. So, since you have passed the test, and for those who did not pass the test and did not realize that what I had drawn was actually incorrect, then listen up. The configuration that I just showed is incorrect, and now I'll show you the correct drawing. So the diodes are actually arranged in this manner for the diamond. And let's start again with this part, helping you to understand how this diamond works. All right. So current flows like this. Okay. Then the current reaches this node, and then it has an option to go either here or here. But in this case, it can't go here because it gets stopped by the diode. So let's move on. Current flows, and then it reaches here. So now again, it reaches a choice. It can either go here or here. But in this case, it can't go here because it's blocked by the diode. So it just goes on. And then in this case, I suppose it goes through the voltmeter, and then we get the reading for the voltage output of the diamond here. So it goes back, then it goes through here and it meets this node. So now it has a choice. The current can either flow through here or here. In the case where it goes down, it goes to this node. Yeah, it goes to this node and then it completes the circuit here. At these two nodes, it does appear that there is the option to go through the diodes again. But I'm pretty sure this won't happen because at this point, right, it's already so close to grounding. Why would it want to go through this resistive area? So again, electricity follows the path of least resistance to ground itself. So why would it go through the entire diode loop again? Therefore, it won't follow these two paths here. It will just go to the AC power source here and ground itself. So this is in the positive case where the output is coming out through here. So let's look at the other case where it is negative. So in negative it will be here. So okay, the voltage comes out here. Okay. Then it reaches this node and it has a choice whether to go up here or up here. And in this case, this diode blocks this path, so it has to go through here. Then it reaches this node and it again has a choice to go through here and here. Blah blah blah, this is blocking the current, so it has to go down. Goes through the voltmeter to get this reading. Then it goes through here, then it reaches this node. And it has a choice to go either here or here. Again, it won't go through here. Because the path of here, right, to get itself grounded, the current grounded, is very resistive, and it's easier to go through this diode, reach this node, and go through here to ground itself than to go here to go here. That's why it doesn't follow those paths. Then it goes through here, it gets grounded. So that's how the diamond works. That's how it gets all these hills here and gets them into the positive side. Recall with the half-wave rectifier, it is not, when you put in 100 volts, it is not 100 volts peak as the output. There is some voltage lost due to the fault voltage of the diode. And of course, the entire wave does not get grafted completely. There's still this bit here that's missing because the voltage was lesser than the fault voltage of the diode. Well, the same thing applies here. Because all these diodes have a fault voltage, right? And as such, the voltage oh man. Alright, as you can see, yeah. What was I saying? Oh yeah. The voltage obviously is not going to be 200 volts peak here, and there's actually going to be some lost. But in this case, it's not just the fault voltage of one diode, but it is the fault voltage of two diodes. So in the case where the voltage is positive, right, actually two diodes are powered. So let's run that back again, right? It goes through here, it powers it powers that diode, it comes back here, it powers this diode, and then it grounds. So two diodes get powered. As such, right, the voltage needs to overcome the forward voltage of two diodes. And then the same thing here, why this is not present is because when the voltage is lesser than the forward voltage of two diodes, then the output won't be anything. So that's the diamond bit, finally. Alright, now onto the capacitor. The capacitor actually smoothens this. So we are close to getting DC already, but this is a goofy R looking DC. What we want is a line. But now we have these hills. So the first step to getting the flat line that we want is with a capacitor. So a little recap. A capacitor is a component that can store charge, and then when it's grounded, right, or it's connected to itself or whatever, it expels the charge. Yeah, it pushes out the charge. So when we connect the capacitor, the waveform goes from this to this. It becomes smoothened. Keyword smoothened. You need this word for your exams. You need to say smoothened. So the capacitor smooths the hilliness of the output of this diamond of diodes into this less hilly thing. I don't know what to describe this as. Okay, it smooths the output. Yeah. So how does the capacitor do this? So as you can see, right, it's directly connected to the output of the diamond of diodes. As such, when the output is high, like this bit here, it actually charges the capacitor. So when the power is low, the capacitor goes like, oh my gosh, this is my time to shine. And then what it does is it just expels all its charge. So this bit here corresponds to this part here. So when the voltage is completely low, it just shits out all the charge. And then it leads to this more like a line output. Yeah. So that's that. And we are finally one component away from getting this sweet DC output. Alright. So now we reach the Zener diode. I suppose the Zener diode and the resistor, those two components are required for each other. Yeah. So what the Zener diode does is basically it clamps down the voltage of the output of the capacitor, and it lets us get this straight line here. How does it do that? So as a little recap, the Zener diode has something known as a breakdown voltage, and if the voltage across it, right, because, okay, and note here, right, is in reverse bias. So the voltage in this case, this line is positive. This line is positive because in all cases of just now I showed you, the output, like in this case, the output goes here. In the other case, the output still goes here. So this line actually is the positive line, the positive rail. And you can see that this diode, this Zener diode is in reverse bias. So the Zener diode actually has a voltage known as the breakdown voltage, which is when the voltage across it in reverse bias, right, reaches a certain point, then the Zener diode goes like, okay, you're not increasing anymore, and then it clamps down the voltage. So basically, when it reaches a certain point, it just clamps down the voltage, not allowing the voltage to be any higher. Okay, how does this help us? So the breakdown voltage in this case will be tuned to like around here, this part of the capacitor line. So you see all this hills part, right? There's only one part of this signal that actually is in this line. So what happens to the rest of the hills? Here, these little hills, what happens to them? Simple. It gets clamped down, as I already said 15 trillion times. The Zener diode clamps down the voltage. So, it clamps down the voltage here, and then look at this. That was it. That was the DC output, which we see here. So, okay, I suppose we have one last component, which is the resistor. So, what's the point of the resistor? Basically, you can't just pull down the voltage like this. You actually need to consume it, you need to use it to do something. So what the resistor does is that the Zener diode goes like, okay, resistor, hey, I need to clamp down the voltage, there's extra voltage here, so can you go and eat this up? Then the resistor's like, oh, okay. So the voltage in the resistor turns into heat lah. It gets dissipated off as heat. Why is the resistor required? If you remove the resistor, then the extra voltage actually gets turned into heat in the Zener diode, and that's not good, because if like your Zener diode overheats, then it breaks, and you wouldn't want that. That's stupid. So that's why you need the resistor for safety. Okay, so that is the full bridge rectifier, and like every single stage, there are 3 stages. All right, and that's pretty much all you need to know for rectifying AC. So thank you for watching.